Hello everyone, my name is Manuel de los Santos. I'm the product manager for biological processes at Aerobic Systems. Joe Tardio, which is the product manager for AquaNereda, will join us a little bit later during the presentation, and we will talk about activated sludge to granular sludge, specifically an overview of time-based biological treatment technologies. We will talk about an overview and advantages of the time-based systems, followed by 3 different technologies that define the different time-based systems, which include activated sludge, granular sludge, and densified sludge. On each one, we will have a definition of an operation of the system, components of the system, and then an installation profile, followed by a quick summary of the presentation. In terms of treatment technologies and the design considerations, what you're looking at is a spectrum of suspended growth. And as you can see in the screen here, you can see conventional activated sludge, densified sludge, and aerobic granular sludge, and they are defined by the different size of particles. So you have all the way from pin flock to large granules, and all in between, then you have the densified sludge. So if you look at the activated sludge systems, you can see how there's particles all the way across the slide here. Then you have densified sludge where you have a little bit larger particles around. And granular sludge, you can clearly see the difference between all 3 technologies. So what we will discuss is AquaSBR system for activated sludge. We will talk TruDense for densified sludge, and we will talk AquaNereda for granular sludge systems. Now, if you look at design considerations for each technology and compare to other different technologies, especially, let's start with footprint. So the worst case scenario for footprint would be BNR. And BNR, you can see, let's assume that that's 100% of the footprint. If you compare that with an SBR, you would be at 50% of the footprint compared to a full multi-stage BNR process. And then we keep going through the technologies. Densified sludge, since you can settle better and have a little bit increased mixed liquor concentration, you can make it a little bit smaller, so about 40% of a multi-stage BNR process. Then we have, for example, an IFAS system at about 60% of the footprint. MBR and granular sludge are the base case scenarios in terms of footprint at about 25% of multi-stage BNR. And the main reason is because you can increase the mixed liquor significantly and shrink the system to make sure that you can do the same treatment in a lot smaller footprint. Now, in terms of energy, while MBR and granular sludge are in the same plane for footprint, energy is completely different. So you have worst case scenario then is MBR for energy consumption. You have a lot more aeration, you have a lot of recycles from the membrane tanks back, and all the recycles for nutrient removal. BNR at this point becomes about 70% of the power consumption for treatment system, followed by IFAS. Then densified sludge, you still have a little bit higher mixed liquor concentration, so you may have a little bit bigger mixers. And then SBR at about 50% of an MBR, and then aerobic granular sludge at about 40% being the best case scenario. In terms of life cycle cost, if you look at a 20-year life cycle cost analysis, the worst case scenario again would be an MBR system. At that point, densified sludge become about 80% of that with, in terms of life cycle cost, IFAS about 90%, BNR multi-stage about 80%, SBR 75% or so of the life cycle cost, followed by aerobic granular sludge at about 50%, which is the best case scenario again. Now, if you look at a time-based treatment specifically, what we're looking at, and what I'm going to do here is give you an overview of the different treatment technologies required in order to do nutrient removal in a system. And I'm going to calibrate you in terms of what are the processes required separately, and then I'll talk about what the advantages are for time-based activated sludge. So if you need BOD, TSS, and nitrification, you would need an aerobic tank, a clarifier, and return sludge. So that's a pretty good system to do BOD, TSS, and nitrification. If you need denitrification, now you're looking at recycle back to an anoxic tank, taking full advantage of the influent carbon, and now we're recycling back 3 to 5Q at this point. If you need total phosphorus removal, now we're looking at an anaerobic tank in order to create fermentation, release phosphorus into the water, and which will be taken back up in the aerobic and anoxic tanks after for luxury uptake of phosphorus. If you need even better phosphorus removal or total nitrogen removal, now we're looking at secondary aerobic, secondary anoxic, chemical addition, potentially carbon addition for denitrification, and potential chemical addition for phosphorus removal, for phosphorus precipitation. Now at this point, you're looking at a 4 to 6Q recirculation. So when you're looking at time-based technologies, what we're looking at is innovative technologies to do the same treatment that you can do in space, but not by time. So at this point in batch systems, we're looking at potentially removing recycles, reducing or eliminating chemical addition, and lowering the footprint. So how can we do that everything by time instead of space? I'm going to go through a few operational flexibilities in the system and how we can achieve that effluent in a time-based system. So one of the first ones would be operational flexibility. So we're looking at time-based system where you have the capacity to modify the cycle. So you have a single tank, and in that single tank, we're changing the conditions in the reactor. Instead of moving the water around the plant, you're just changing the environment. So you could have an aerobic environment at the beginning, then you have a react phase where you can be aerobic or anoxic, and then you have a settle phase. So at this point, if you need more anaerobic conditions, what you simply could do is extend that anaerobic conditions in the system in order to do sludge conditioning or even more enhanced biological phosphorus removal. If something toxic comes in and you're not settling really well, you could potentially just increase the settle time in order to settle for a longer time rather than actually changing the size of the tank where you would need in a flow-through activated sludge system. In addition to cycle modification, you can change the aeration times. So if you have a total nitrogen requirement, you can do nitrification, denitrification, but the conditions in the influent may change. And if they change, you can literally change your aeration times on and off in order to, or extend aeration times on and off in order to do better the nitrification, denitrification to accommodate what influent nitrogen is coming in. Then you have flow and loading equalization within the same reactor. Everything happening in the same reactor by batch. So let's say that you have a diurnal flow variation like you see on the screen here, and you will have different batch sizes in the system. So what happens is throughout the day, you may have different batches, but the loading is equalized because you're bringing the water in, you're trapping that water in that batch, and then having a react phase to treat that batch that came in to the maximum treatment capacity. So that's another one of the advantages of batch systems. Next is mixed liquor concentration. So in terms of mixed liquor, even with the activated sludge, so we saw activated sludge, densified sludge, and granular sludge. Even in the activated sludge, we can afford a little bit higher mixed liquor concentration because there's no flow coming in while settling. So you could have 4,500 mixed liquor in an activated sludge system all the way to about 8,000 or even 10,000 milligram per liter in a granular sludge system. In terms of instrumentation feedback, so since everything happens in the same reactor and you're changing the conditions of the system, you can measure all the parameters in the system. And we're talking ORP, dissolved oxygen, you can measure mixed liquor, you can measure ammonia, nitrates, but everything happens in the same tank, and you're literally just changing the conditions of the reactor, and you can measure what happens and give instant feedback to the system to react right away on those parameters. So again, we're reading over time instead of space. So with a single instrument, you will be able to control the system a lot more accurately. In terms of basin geometry, any basin geometry would work here. So you could have square or rectangular tanks, you can have circular tanks, or even annular shaped tanks. The only thing that we need to do in a batch system is make sure we're mixing the tank either with the aeration system and distribute the air throughout the tank, or with separation of mixing like in an SBR system. In terms of effluent quality, all the batch systems will be able to meet 10 milligram per liter of BOD and TSS, 3 milligram per liter of total nitrogen, which happens biologically, and then total phosphorus of 0.5 milligram per liter with small amount of chemicals. The chemical addition will depend on the system. For example, granular sludge would be way better at phosphorus removal biologically, so less chemical is needed. Now let's start with the first technology, which is activated sludge in the form of an SBR, what we brand AquaSBR, true sequencing batch reactor. And what this is an activated sludge system. And the main features of this process are true batch. And the main thing here is that we're bringing the flow in, trapping that batch, and treating that batch to the maximum treatment capacity during a react phase, settle and decant phases with no flow coming in. So that's what we call true batch. It features separation of aeration and mixing. So the aeration system is designed for the aeration, for the oxygen only, and the mixer is designed to completely mix the tank without the help of the aeration. So that helps us make sure that we can mix the tank completely during anaerobic treatment without aeration. And then when you need to cycle aeration on and off to do nitrification and denitrification, then we turn the blowers on and off. It features a floating decanter. So whenever you're looking at an SBR, one of the main features would be at the decanter, which is the one piece of equipment that converts the entire reactor into a secondary clarifier. So again, we're doing the phases within the same reactor, and decanter is a very, very important part of that and all the design features. And lastly, time-based control. Since everything happens in time, we do have PLC control panel included in the system in order to go through all the different phases. And the different phases include mix fill. So at this point, flow comes in, mixer's on. So we want to create anaerobic conditions in the reactor to create fermentation, volatile fatty acids, and phosphorus release. The next phase in the same tank is react fill phase, where the mixer is still on, flow still coming in. Now we cycle the aeration on and off to do nitrification and denitrification, taking full advantage of the carbon that is still coming in the influent to do denitrification. Then is where we call true batch process. So we stop the flow from coming in. We will send the flow to the next reactor, which will start mix fill phase. And this goes into the true batch phase, which is your react phase. In react phase, we trap that batch that came in and we treat that to the maximum treatment capacity, turning the aeration on and off to do nitrification, denitrification. But more importantly, at this point, you don't have a lot of carbon, or any more constituents. So most likely it will be the phase where we will save more power by turning the blowers off and let the mixer mix the tank a lot more efficiently than the blowers. Then we go into settle phase. In settle phase, there's still no flow coming in. Everything turns off, so it's completely quiescent environment in the system. So some operators will call this a perfect clarifier. So simply just settling down for about 45 minutes and then go into the decant phase in the same tank, where that batch that came in, that is about 30 to 40% of the reactor, we will have that clean water out through the decanter. Note that we are discharging from the subsurface, so any potential floatables are not going into the decanter. There's dual means of sealing the decanter and a lot of other features that we have for that decanter. In terms of the main components, I mean, you could have valves, pumps, instrumentation, but the main components that make an SBR that you want to look for are aeration and mixing, specifically separation of aeration and mixing with a very efficient mixer, and aeration. So the aeration is designed for aeration for oxygen only. And in this case, you can see retrievable diffusers, which can be pulled up from the tank individually and be able to service the diffusers without the water in the tank. You can also see the decanter and the quality of the equipment. So mostly stainless steel in the system. And again, like I mentioned before, all the features that you would have for a decanter in order to have clean water at all times out. And then the control system would be the next main component, because it's what has the cycle structure and the strategy of operation of the system, which will give you all the advantages that we talked about at the beginning. Now, for installation profiles, what I'm looking here at is a comparison of an SBR with a multi-stage BNR, in this case, a modified Barden-Foe. So you can see a small system about 0.5 MGD, and you can see the different configurations, different tanks, pre-anoxic, anaerobic, aerobic, and then reaeration, post-anoxic. So you can see all these systems and associated recycles with that. In addition to that, you have secondary clarifiers. So all that, if you look at an SBR system and a small 500,000 gallon a day plant, is a 2-basin SBR system and a post-equalization. So everything happens by time. You're alternating treatment between one SBR and the other. And then we have a post-equalization in order to slow down the flow for the processes after. But still, a lot more flexibility, a lot simpler than a multi-stage BNR process for the same or better effluent. Now, Joe Tardio will talk to you about aerobic granular sludge technology.
Hey, thanks, Manuel. Good to be with you all. So let's get into the AquaNereda aerobic granular sludge technology. A little bit about aerobic granular sludge. First, it is a true microbial biomass. What we mean by that is that there is no external plastic or other media carrier added into the system in order to facilitate biological growth. It is a fully sustainable process. So the granules are grown from 100% biomass that's generated within the system itself. Each granule, by definition, must be at a minimum 200 microns in diameter. We'll speak a little bit more about why that's important in the next several slides. And the sludge is particularly robust and resilient to things like process upsets or toxic shocks. The second important category in terms of defining aerobic granular sludge is its settling characteristics. And when we discuss settleability of aerobic granular sludge, we compare it to conventional activated sludge that Manuel just discussed. It settles in the same time in 5 minutes that conventional activated sludge typically takes around 30 minutes to settle. And by virtue of its superb settling characteristics, the system is able to be designed at roughly double the mixed liquor suspended concentration of 8,000 milligrams per liter, therefore significantly shrinking the size of the bioreactors and the entire system. That enables the system to treat more capacity in a much smaller footprint. And the third, the ability for the system to achieve inherent BNR, biological nutrient removal, in a single process reactor. And this is done in time by being a batch cycle, and also in space throughout the actual granule itself. And that's why that minimum granule diameter is so important, because it allows for the formation of discrete aerobic, anoxic, and anaerobic zones within each granule. Essentially, each granule is its own mini wastewater treatment plant, allowing for the reduction of total nitrogen down to 3 milligrams per liter and biological phosphorus removal down to less than 1 milligram per liter without chemical addition. We hit on the settleability and the settling characteristics of granular sludge compared to conventional activated sludge, and this is kind of a nice visual representation of what that actually looks like in a 5-minute settle at 8,000 milligrams per liter on the sample to the left versus settling over the same period of time at roughly half of the mixed liquor suspended solids concentration. Touching on the cycle structure, similar cycle structure to what Manuel discussed, a little bit different. We'll talk about some of the differences here. The first of three phases of the AquaNereda AGS cycle is the fill draw phase. This is a simultaneous fill and draw of the bioreactor. The second phase, the longest of the three phases, is the react phase. This is where aeration is being cycled on and off, both to achieve mixing as well as to achieve certain aerobic or anoxic conditions, depending on the treatment requirements. And the third is a short settle phase, again, by virtue of the superb settling. The granules settle very quickly, as well as the inclusion of a selective wasting portion of this settle phase, and then on to the next cycle. What's particularly important to note are the conditions in the reactor during each one of these phases of the cycle. The fill draw phase is done under strict anaerobic conditions, and that's important for sludge conditioning, as well as the growth of phosphate accumulating organisms, which secrete the EPS that are so important to bind particles together in granule form. In the subsequent phase, in the react phase, as we discussed, based on cycling on and off of the aeration system, achieving certain aerobic and anoxic conditions in the reactor, which allowed for that stratification across the granule diameter, aerobic zone being created in the outermost portion of the granules, and anoxic and even anaerobic conditions on the innermost portion of the granule. We mentioned that secretion of EPS from the phosphate accumulating organisms and its key role in terms of aggregating smaller particles into larger particles, and those larger particles aggregating into eventual granules. And this is kind of a schematic showing how that actually occurs over time. And one thing to note when we talk about seeding here, we're not talking about the addition of granules from another facility. We're actually talking about seeding with conventional activated sludge and the granules forming naturally throughout the ongoing cycle structure that the Nereda system employs on the sludge. Again, we speak about a true microbial biomass developed within the bioreactors as part of the system, formed from, again, that conventional activated sludge. And what that means is that it's sustainable. There is no replenishment of the media that is required, and the sludge continues to grow in granule form by virtue of the cycle structure and the sludge conditioning, as well as the selection mechanisms that are employed by the cycle that we will discuss in this next slide. So through many years and decades of practical application, research, the community has identified 6 selection mechanisms that are responsible for the formation of aerobic granules. And why this is important is several reasons. One, to note that the Nereda process employs all 6 selection mechanisms automatically as an inherent part of the cycle structure, but also to note that several of these are actually employed in the densified sludge treatment process that Manuel will speak about later in this presentation, called Aqua TruDense. Let's talk about those first 2. The first being the hydraulic selection for fast settling particles. And what we're talking about there is actually the physical wasting of poor settling sludge every cycle that is employed, and that is done typically in that settle phase. The second selection mechanism being the biological selection of EPS forming microorganisms, and this again is the anaerobic conditioning during the feed phase, where PAOs are given a preferential advantage and allowed to outcompete the ordinary heterotrophs. By selecting for those PAOs, we allow for the growth of, or the secretion of, the EPS biopolymer that allows for the granule formation. When we talk about granule size, we talk about it because there are some significant implications and advantages to having not only very large granules, but granule size that span the full spectrum from the very smallest of the definition 200 micron all the way to 3, 4, even 5,000 micron or 5 millimeter granules. Why do we care about the size of the granules? The first is settling velocity. This is the most obvious. The larger the particle, the more spherical the particle, the faster it will settle. The second, we touched on this during the sludge conditioning, is the concentration of beneficial microorganisms. So it's been shown through DNA analysis that the concentration of beneficial microorganisms in an AquaNereda system, meaning denitrifying organisms, nitrifying organisms, especially the phosphate accumulating organisms, are found in much higher concentrations than in typical activated sludge systems. And the third is that it's been shown time and time again that the granular sludge is much more resilient to process upsets, things like pH swings, load swings, temperature variation, when compared to conventional activated sludge systems, again, because the granule acts as a protective shield in some way for those microorganisms to be protected from the adverse process conditions that may exist in the reactor. We'll now discuss an installation of the AquaNereda Aerobic Granular Sludge technology that shows some of its main advantages. This is the installation in Foley, Alabama. The challenge here being that the previous plant, which was a conventional activated sludge plant that relied on an oxidation ditch process, was up against its rated capacity due to population growth. They had some significant footprint limitations in terms of how much they could actually expand on the current site. They were also expecting a more stringent permit in terms of nutrient limits, and they also wanted to look for a process that was hopefully more resilient against salinity intrusion. This is a plant in the Gulf Shores of Alabama that does have some salinity impacts from time to time. The solution that the owner elected here was the installation of an AquaNereda aerobic granular sludge system that's comprised of these 3 circular reactors that we see in the photo here, utilizing the existing oxidation ditches really just for some sludge storage, but really decommissioning a majority of that older plant, with plans to expand up to about 10 MGD on the existing site, which would not have been possible had they stayed with a conventional process. The outcome here being that they were able to significantly increase their treatment capacity on their current site. Their energy costs have been reduced by 40 or 50%. They have met and actually exceeded their requirements in terms of nutrient removal. And as a result of all this, the plant actually won the 2021 Global Water Distinction Award for Wastewater Project of the Year, competing with plants from all over the world. This plant has been in operation since January of 2020, up and coming its 5-year anniversary, which is something that the owner, as well as Aerobic Systems, is very proud of. You could see here the performance of the system, producing very, very high quality effluent, meeting and as I mentioned, exceeding the required nutrient limits that they do have in their permit, achieving fully nitrified effluent, very low levels of BOD/TSS, very low nutrient in the form of nitrogen as well as phosphorus, with no chemical addition to the bioreactors. But one thing that's of particular importance is showing just how much capacity they were able to get out of a much smaller footprint when compared to the previous conventional activated sludge system. So you could see here on the left the AquaNereda system producing significantly more flow in less process volume and in about a third of the footprint that the previous plant took up. With that, we'll go back to Manuel to discuss a little bit about Aqua TruDense.
Thanks, Joe. Now we're looking at Aqua TruDense, which is our true batch densified sludge technology. And we start with a definition of densified sludge. So it is a process of intensification method We're concentrating biofilm aggregates, therefore organic loading capacity, and improving the settling characteristics, so the hydraulic loading capacity. Now, in a general approach, you're looking at selective wasting and organic selection, pretty similar to what Joe explained with granular sludge. So we're looking at selective feeding, selective wasting, therefore high food to mass ratio at the beginning of the cycle, and that results in increased mixed liquor concentration and while having improved settling. In terms of advantages of TruDense or densified sludge, you can see here a full profile of aerobic granular sludge, and densified sludge fits in the first category of granules, kind of smaller particles, and it will be combined with activated sludge. So it will feature all the benefits that I talked to you about on the SBR system, but then you have process intensification with the densified sludge. And we have improved settling, and we can increase the mixed liquor by 20 to 25%, therefore lowering the footprint compared to flocculent sludge or activated sludge. So where does this fit? So you're looking at a sequencing batch reactor, activated sludge. You're looking at granular sludge with the AquaNereda. We would fit right in between that. So if you're looking at 4,500 mixed liquor in an SBR and about 8 to 10,000 mixed liquor on a granular sludge process, densified sludge should fit about 5,500 or 6,000 milligram per liter or so. And definitely look forward to more information during WEFTEC 2024. Now, the key design components in the system would be the same as SBR. So you're looking at a decanter, very reliable decanter. You're looking at aeration and mixing designed for separation of aeration and mixing, and still the control panel. Now, the difference would be now we're incorporating an influent distribution grid in order to have more substrate throughout the system at the beginning of the cycle, and then we have selective wasting in the system, and then variation of an SBR control strategy in order to form densified sludge. And now I pass it on to Joe to do a quick summary of the presentation.
Thanks, Manuel. So, in summary, what have we discussed today? Well, we've discussed the full spectrum of suspended growth technologies, including activated sludge, densified sludge, and granular sludge, and the systems that incorporate those different types of sludges and the benefits and advantages of such. The aspect of time and space management, we discussed the process of managing the treatment of discrete batches in time rather than space, as typical conventional BNR processes do. But we also spoke about the aspect of space in terms of the AquaNereda granular sludge process, whereas nutrients are treated in the space of a granule instead of in the physical space across footprint in a wastewater treatment plant. The commonality of all of these treatment technologies from the standpoint of all of these processes are occurring in a single process reactor without the need for clarifiers or return piping and pumping. The aspect of the ability for the batch systems to treat flow and load variation within the bioreactors themselves, again, by being time-based systems. The flexibility that these time-based cycles offer an operator in terms of full control of the influent flow as well as the treatment of each and every batch to the requisite treatment standards. And of course, at the end of the day, what are we always seeking? The ability to achieve the lowest life cycle cost, not only from an equipment standpoint, but from an operational cost standpoint, a construction cost standpoint, an ease of operation standpoint. And what we see as commonalities, even though these technologies all offer slightly different benefits and are applied in slightly different formats, the commonality being that they can offer the very lowest life cycle cost to an end user when considering all of the capital as well as operational costs. And now we'll move on to our question and answer session. Thank you so much.